Frequently in conversation we hear people use the term correlation. You'll hear somebody say, well, I don't see the correlation there, or those two things have no correlation. Well, what we're going to find out is that there's actually a calculation that goes behind the term correlation. Before we start, I want to talk about some of the basics that you're familiar with and should help understand a little bit where correlation is coming from. So first of all, we have over here x minus x bar. And if you remember way back when we were doing standard deviation variance, that we know that the x minus x bar is the deviation. So we are looking for the deviation between the x value and the mean of all the x values. In this case, we have copier sales of America data, the number of calls made, and the number of sales made. So what we're looking at is how are these two related, or if at all. In this case, I've already filled in some of the formula values here, so you should be familiar with how to do these. This is just the sum of all of the x variables, sum of all the y variables. The mean of the x variables, the mean of the y variables are here, and then the standard deviation formula right here. And we can put in the count as well. And we have 10 items. So when we look at the deviation, we take, let's say, Tom Keller, who had 20 sales calls, and we have a mean of 22. So we take 20 minus 22, and we see that there's a deviation of -2. In order to get the variance, what we did is we took that value and we multiplied that by itself. In other words, we squared it. Or another way to write that would be to put x minus x bar times x minus x bar, and then we summed those variables up. Then we divided that by n minus 1, and that was our variance. And the idea behind that is that if there are two variables that are related, then we expect that a change in one of those variables should elicit a similar change in the other variable. Here, in this example for variance, we're multiplying the two x minus x bar values together. Well, in this case we have two different variables, so instead we can go ahead and multiply the x minus x bar times the y minus y bar, because if we believe that these two are related, then multiplying them together should indicate some of the change that occurs to the variables. Now, what you see here is the formula for what's called covariance. And covariance is a measure of how the two variables are related. With the variance, though, we want to get an average value of the combined deviations. So what we're doing, that's why we're dividing it by the n minus 1. Now, this will give us a value that tells us something about the relationship between the two variables. So we could do all of each of these values, 20 minus 22, 40 minus 22, 20 minus 22, and then do the same here, 30 minus 45 for the y minus y bar, and multiply all those together and divide them by n minus 1. The problem with the covariance value is that it is based on, or it's dependent on the scales of measurement used. So instead of saying number of sales here, let's just say for an example that we had sales in dollar here. Well, if we did all of these calculations to find the covariance out, it would give us a certain value, and that would give us some indication of the relationship between the two variables. Now, if we changed this from dollars to euros, and I'm not going to try to write the euro symbol, that would change each of these y variables, and hence the covariance will also change. So it becomes a little bit more challenging to relate the two covariance values, or to relate the two associations between to relate two different variations. So in other words, if we had this group of folks sales data, and if we did it, and this was US dollars here, and then we had a similar group of sales representatives in Europe using the euro, we would get two covariance values, and they could be the exact same covariance, but the relationship is completely different. So what do? Well, we standardize the covariance formula, and the way that we do that is we add in to the denominator the standard deviation of x times the standard deviation of y, and we get what's called the correlation coefficient, or Pearson's R, or the Pearson Product-Moment Correlation. And why do we use the letter R? Well, to talk about a correlation coefficient, well, because statistics isn't hard enough, we have to throw a confusing variable letter in there for you. So before we go into doing the actual correlation coefficient calculation, the first step that you usually do when you want to do a correlation is you want to take a look at your data to see what it looks like. And so how do we do that? And in Excel, it's pretty much a three-step process. After your data is selected, there are 3 clicks that you do. You go to Insert, Scatter, and whichever scatter chart you'd like. The first one is the one that I picked. And we can see that the data generally kind of slopes upward. And this could use a little bit of cleaning up, putting in axes, labels, and so on. But for the sake of the video, we'll just leave it as is. And so based on this, it appears as though as we increase the number of sales calls, we also increase the number of sales that we make. And that seems logical, seems reasonable. What we want to find out now is how strong of a relationship is there between the two, or a correlation between the two. And just as an aside, we'll go in here, look at the add-ins to the Megastat, go down to Correlation, Scatter Plot, and you can see that I already have the data in there, but let's just take it out. So remember with Megastat, we don't get the labels, just the actual raw data. So we have our horizontal axis, and remember we generally put the X value along the horizontal axis. And then we put in a chart title, and I've already done that. By default, it'll have the plot the linear regression line on there, but we're not getting into the regression at this point, so we'll just leave the linear regression line off. And you can leave the display markers as the default. Hit OK. And as you can see, we'll copy this over. Megastat makes a slightly prettier graph, but it is the same data, so you see essentially the same slope that you see in the Excel raw information. Since we have this really fancy Megastat graph scatter plot that has the labels and the title in it, we'll go ahead and delete the Excel chart because we don't really need it at this point. And we've already taken a look at both of the different types of scatter plots to see what type of relationship it looks like graphically. So let's go down to moving it to calculating our correlation coefficient. So the first thing we have to do, basically the same type of thing that we're doing with variance, is we have to calculate out the x minus the x bar. So our x value here, our x bar here, we hit F4 to make the x bar, or the mean variable, a fixed cell reference. And just as we said before, Tom Keller, x minus x bar is equal to -2. Now, we don't need that. As we did with the x minus x bar, we do the same thing for the y minus y bar. We take the y value for each of the sales reps, subtract from it the y bar, we hit F4 to make it a fixed cell reference, and we calculate that out all the way down. Now, as we see up here, we take the x minus x bar, multiply it times the y minus the y bar. And we do that for each observation or each sales rep in this particular case, and we get a total or a sum of the x minus x bar times the y minus y bar, which is just, as I did here, summed up these numbers. We get 900. So our numerator in this particular case is 900. So for our calculation, we know that we're going to go ahead and use the formula that we have here. So we can just take our numerator, which is the F12 cell, then we divide it by what? N minus 1. N is 10, so n 10 minus 1 is equal to 9, but for the sake of argument, we'll put it in. And then we multiply that times our standard deviation of x and our standard deviation of y, and that should be about right. Oh, got to put in an extra parenthesis here. That's why. There we go. That should do it. So what I had failed to do was encapsulate the entire denominator in a set of parentheses. So what it was doing is it was taking my 900 divided by 9 and then multiplying it by the 2. So now that we've fixed that, we see that our correlation coefficient, our Pearson's R, is 0.759. Now, as I said before, the correlation goes from a -1 and it goes through 0 up to a +1. But the point to take away here is that when we say it's positive, that's the direction of the grouping of the data points. So it goes upwards for a positive number. And that is also referred to as a direct relationship. If we had a negative relationship, it would go in a slope in the opposite direction. It would go a downward slope. It doesn't mean that one is necessarily better than the other. In this case, it makes sense that the number of sales calls, as the number of sales calls increases, the number of sales increases, but there may be a case where, let's say this was instead of calls, it was number of interruptions while on a sales call. Well, the more interruptions you get on a sales call would probably make your sales go down, so you'd have a slope like this. But if the number of interruptions related to the number of sales, the correlation coefficient also became 0.759, but it was a negative 0.759, like that. The relationship would be as equally as strong. It would just be that one is negative and one is a positive relationship. So the strength is the actual absolute value of the number. And there are different determinations on what is considered a strong or a weak relationship. But if in the social sciences you are very unlikely to get a relationship of 1.0. Well, you will not get a relationship of 1.0, and you're unlikely to get one much greater than about a 0.80. But again, those are sort of heuristics when it comes to what is considered a good relationship or a strong relationship and what is not. And you can use different values to determine that. In the social sciences, though, in general, if you've got 0.8 to 1.0 correlation, that's considered a very strong relationship. Again, if it's negative 0.8 to negative 0.1, that also would be a very strong relationship. It would just be an indirect or negative relationship. 0.6 to 0.8 is a strong relationship. 0.4 to 0.6 is a moderate relationship. 0.2 to 0.4 is a weak relationship, and 0.0 to 0.2 is a weak or no relationship. Okay, so we're finding out some really exciting information about the Copier Sales Company of America here, but let's not get too far ahead of ourselves. I have a couple of cautions for you when it comes to the correlation coefficient. And the first has to be the direction of causality. Actually, causality in and of itself is a caution for you. Because we have a relationship here that as sales are increased here, calls also increased, that doesn't mean necessarily that an increase in the number of calls a sales representative makes will also increase the number of sales that the salesperson gets. That's what's called causality. But what we aren't taking into account is that there may be other variables that are involved. Those other variables might be the number of walk-in customers that affect the sales. There may be the time of day that the calls are made. It may be the time of year that the calls are made. So there are other variables that may be a factor in the relationship. So you cannot assume that the correlation means causation. And this other caution that I have for you is in the direction of the causality. We have the value of 0.759, which indicates a direct or a positive relationship. So it appears that as we increase our sales calls, we increase the number of sales that we have. However, there is no statistical reason why we can't say that as the number of sales increases, our number of calls will also increase. In other words, there's no direction indicated by the correlation coefficient. So those are two cautions for you. The first is actual causality, sometimes called tertium quid. In other words, there could be other variables that are in play that are affecting the sales output or the number of calls. And then the other is the direction of causality. Well, that wasn't too difficult. Now that we're done, we can move on, right? Well, no, not really. Because what we found is that the correlation coefficient of 0.759 is between the number of sales calls made and the number of copiers sold. But only 10 people were sampled. And I kind of kept this a secret, but the total number of salespeople in the Copier Sales of America company is greater than 10. So this is just a sample of our data, and you could have figured that out because we used the sample standard deviation, but that's beside the point. So the population is all the salespeople in the company. So is it possible that the actual correlation for the population is 0, that there is no relationship between calls made and number of sales? Well, that would mean that the 0.759, let's get rid of this fake number there, this 0.759 correlation that we got was due to chance. So what do you think we should be doing next? Well, it's probably coming to you, but it's the hypothesis test. So let's see if this will work here. There we go. So our null hypothesis is that rho, which is the population correlation coefficient, that's a rho, is equal to 0. The correlation of the population is 0. And our alternate is that the rho is not equal to 0. The correlation in the population is not 0. So what we're going to do is we're going to reject the null hypothesis if our t statistic, or our t test statistic, is greater than our t critical value. And what's our t? Well, I'm glad you asked. Here is our test statistic. Again, what we're testing is, did the sample data that we pulled to calculate our correlation coefficient come from a population that has 0 correlation between the number of sales calls made and the number of sales? So we're going to reject, again, if t is greater than the t critical value, the positive t critical value, or if the test statistic that we come up with is less than the negative t critical value. To save us a little bit of time, we're using the alpha equals 0.05 level of significance, and you can look this up in the book, but the t critical value is equal to 2.306. So what that means is we're going to reject the null hypothesis if this test statistic that we're going to calculate out is greater than positive 2.306, or if this test statistic that we calculate out is going to be less than negative 2.306. So let's go ahead and start calculating out our t critical or our t test value. So our t value is equal to our r value, which is 0.759, times the square root of n minus 2 divided by, and I closed out the parentheses so that it would be surrounding my numerator, divided by the square root of 1 minus r squared, which is 0.759 times 0.759. And looks like they put in the correction for us for a missed parenthesis that I did. And we get 0.3 or 3.297, lots of numbers after that, but we'll cut it a little bit shorter and we get 3.297. And in this case, we see that our test statistic is greater than our positive t critical value. So we reject the null hypothesis that there is no correlation between the two population values of the sales calls made and the number of sales that we have. One last thing before we go. Let's talk about this r square that's in the denominator of the t-test statistic. It's a simple calculation. We just multiply the r times itself, or the correlation coefficient times the correlation coefficient, and we get 0.58. Well, what is that? Well, the r square is the coefficient of determination. And that's defined as the percentage of variance in one variable that is shared with the variance in the other variable. This will become more important as we get into regression. But for now, this is saying essentially that the 58% of the variance in the number of sales made can be explained by the variance in the number of sales calls made. What does that also mean? Well, it means that 42%, the remaining 42% of the variation can't be explained by the relationship between the number of calls and the sales. And that amount of unexplained variance is called the coefficient of alienation. But we really don't talk about that very often, but we do talk about the coefficient of determination. Well, I forgot. I didn't tell you about how to calculate the correlation coefficient the easy way using the Excel function or the megastat function. So the coefficient of determination actually isn't the last thing we're going to talk about. So let's get down to how we can calculate the correlation coefficient a little bit more easily than manually calculating all of this out. And we'll start out with the actual built-in function of Correl. And all you have to do is type in equals Correl, put in the initial parenthesis, hit the function key or the F sub x key up here, and as usual we get our dialog box for the function. And here we can select the array for calls and the array for sales, and it tells you about it here. Hit OK, and we get a correlation coefficient of 0.759, same as what we calculated over here. Now, another simpler way to do that is if we have the data analysis tool pack installed, we go to the data tab on our data ribbon bar, go to data analysis, select correlation, and here you have input range. You only have one entry. Well, that's because you select both of your data entry or data columns, and then you select labels in the first row if you've done so and selected the labels. And then for our output range, we're going to just go ahead and put that right next to our other value. Hit OK, and let's back that up. We're going to run that again. I forgot that this is giving us the entire correlation matrix, so we'll change our destination to over here so we have enough room. Now what this is, we're not going to get into correlation matrix very much. We'll talk about that at another time. But this is just a matrix showing you what is the correlation for each item. Now if you had more variables involved, this would be a bigger matrix. Since we only have the two variables, you get the ones on the diagonal, because if you think about this, if you were to get a correlation coefficient of calls and calls, we would expect it to be a perfect correlation because it's the same data. And likewise, sales and sales correlation coefficient would be 1 because it's the same data. So the value that's important to us is right here, and that is the correlation coefficient between calls and sales. Finally, we can go into our add-ins, go to Megastat, go down to the correlation/regression menu item, and go to the correlation matrix. Now it's already selected, but remember, when we do this for Megastat, we do not select the labels. Megastat doesn't like that. Hit OK. Goes to our output, and there we have the same correlation matrix that we saw over here little bit different formatting, of course. And then you can see the decimal places go out further than what are indicated here, so they are essentially the same as we have right here.